Welcome! In this video, we are going to begin learning about paths in quivers. A quiver is just a directed multigraph. That means it has points, which we call vertices, and arrows which go from one vertex to another. Our goal in this video is very simple. We want to understand what a path is. A path is one of the most basic ideas in this setting, but it is also one of the most important. We will move slowly, step by step, and build the idea carefully from easy examples. By the end, the notion of a path should feel natural and intuitive. Here is the plan for what we will do. First, we will look at examples of paths of length 0, length 1, length 2, and length 3. Then we will look at examples of strings of arrows that are not paths. After that, we will explore some common features that appear in quivers, such as loops, cycles, parallel arrows, and branching. Then we will ask a very interesting question. When does a finite quiver have only finitely many paths, and when does it have infinitely many? Finally, after we build enough intuition, we will give the formal definition at the end. There is also one important convention for this video. We will read a path from left to right. So if we write PQ, that means we travel along P first, and then along Q. That order matters, and we will keep using that convention throughout. A path is a legal walk along arrows. What makes it legal is that the arrows must fit together head to tail. In other words, when one arrow ends at a certain vertex, the next arrow must begin exactly at that same vertex. For example, if one arrow goes from A to B, and another arrow goes from B to C, then we can follow the first arrow and then the second. That gives a path. So a path is not just any collection of arrows. It is an ordered sequence of arrows that connect properly. That little fitting condition is the whole heart of the idea. Now let us begin with the simplest possible case. A path of length 0 uses no arrows at all. It simply stays at a vertex. So if we are at the vertex B, we can remain at B without moving, and that already counts as a path. This may feel surprising at first. How can something with no arrows still be called a path? But it is very useful to allow this. It gives every vertex its own special path of length 0. For example, if our vertices are A, B, and C, then we have a length 0 path at A, a length 0 path at B, and a length 0 path at C. These are often called empty paths or trivial paths. So every vertex automatically comes with one path, even before we look at any arrows. That is our starting point. Next, let us move to paths of length 1. A path of length 1 is just a single arrow. So if we have an arrow P going from A to B, then P itself is already a path. It starts at A and ends at B, and its length is 1 because it uses exactly one arrow. This is the next simplest kind of path after the length 0 paths. So now we already have two very basic kinds of paths. First, staying at a vertex without moving gives a path of length 0. Second, following a single arrow gives a path of length 1. In fact, every arrow in any quiver is automatically a path of length 1. This gives us a very easy way to begin spotting paths. If you see an arrow, you already see a path. Now let us look at a path of length 2. Suppose we have one arrow P going from A to B, and another arrow Q going from B to C. These two arrows fit together perfectly. Why? Because P ends at B, and Q begins at B. So after traveling along P, we are exactly at the place where Q is ready to begin. That means we can follow P first, and then Q. The result is the path PQ. This is called a path of length 2 because it uses exactly two arrows. Notice again that order matters. When we write PQ, we mean first P, then Q. A path is built by following arrows in a sequence that fits together step by step. Let us now go one step further and look at a path of length 3. Suppose we have three arrows named A, B, and C. The first takes us from A to B. The second takes us from B to C. The third takes us from C to D. Because each arrow begins where the previous one ends, we can follow all three in order. So A, then B, then C gives a path from A all the way to D. We write this path as ABC. Its length is 3 because it uses exactly 3 arrows. So the general idea should now be becoming clear. A path of length 0 uses no arrows. A path of length 1 uses one arrow. A path of length 2 uses 2 arrows that fit together. And a path of length 3 uses 3 arrows that fit together in order. The length simply counts how many arrows we used. Now we must be careful. Not every string of arrows is a path. This is a very important point. Suppose we have arrows P and Q, but we try to write Q then P. To decide whether this is a path, we read from left to right. So first we travel along Q. After that, we end wherever Q finishes. Now the next arrow, which is P, must begin exactly there. But in this example, P does not begin at that vertex, so the connection breaks. That means QP is not a path. This shows us that paths are not just about which arrows appear. They are also about whether the arrows are arranged in a legal order. The fitting condition must hold at every step. The moment it fails, the whole string stops being a path. Next, let us notice something subtle and important. Different paths can have the same starting point and the same ending point. For example, suppose we have two different arrows, A and B, both going from A to B. Then A is a path of length 1, and B is also a path of length 1. They start at the same vertex. They end at the same vertex, but they are still different paths. Why? Because they are different arrows. So even when two paths have the same source and the same target, they do not have to be the same path. This is one reason quivers are called directed multigraphs. We are allowed to have several different arrows going in the same direction between the same two vertices, and each of those arrows gives us a different path of length 1. Now let us look at what happens when a vertex gives us more than one way to continue. This is called branching. Suppose we travel along an arrow and arrive at a vertex B. From B, there may be several arrows leaving. That means we now have a choice. We can continue in one direction, or we can continue in another. Because of that, one beginning can lead to several different paths. For example, after reaching B, one continuation might give the path UX, while another continuation might give the path UY. Both are valid paths because both continue legally from the same place. And from another vertex, we may get yet another path, such as VZ. So branching means that paths are not always forced. Sometimes a quiver offers choices, and each legal choice creates a different path. This is how quivers begin to generate many possible journeys, even from a small amount of data. Now let us look at a very simple quiver. This quiver has several vertices, but it has no arrows at all. So what paths can exist here? Since there are no arrows, we cannot move from one vertex to another. That means there are no paths of length 1, no paths of length 2, and no longer paths either. The only paths available are the length 0 paths. So each vertex has its own trivial path, where we simply stay where we are. For example, we have the trivial path at A, the trivial path at B, the trivial path at C, and the trivial path at D. So this quiver has only finitely many paths. In fact, all of them have length 0. This example is very useful because it shows us that paths do not require arrows in order to exist. Even with no arrows at all, every vertex still contributes one path. Now let us see how quickly things can change. Suppose a quiver has just one loop. A loop is an arrow that starts and ends at the same vertex. So we can travel along that loop once, and that gives a path of length 1. But then, because we end at the same vertex where the loop begins, we can travel along it again. That gives a path of length 2, and then we can go around once more, giving a path of length 3, and we can keep doing this again and again. There is no need to stop. So from one single loop, we immediately get infinitely many paths. 1 trip around, 2 trips around, 3 trips around, and so on forever. This is our first clear example of how infinite families of paths can arise. A loop creates a way to continue indefinitely. Next, let us look at a slightly larger example. Here we do not have a loop at one vertex, but we do have a directed cycle. That means we can start at one vertex, follow arrows through other vertices, and eventually come back to where we started. For example, we may go from A to B, then from B to C, and then from C back to A. That already gives one path around the cycle. But once we return to A, we can go around again. And then again. And again. So we can form longer and longer paths by repeating the cycle. This means that a directed cycle also produces infinitely many paths. So it is not only loops that matter. Any directed cycle gives us a way to keep extending a path without bound. The key idea is always the same. If we can come back and continue again, then there is no maximum length. Now let us contrast that with a different situation. Suppose the quiver is finite, and suppose it has no directed cycle. Such a quiver is called acyclic. What happens then? Because there is no directed cycle, once we move forward along arrows, we can never keep circling back forever. Eventually, every path must stop. There is simply no way to keep extending it indefinitely. And because the quiver has only finitely many vertices and arrows, there are only finitely many possible paths altogether. So a finite acyclic quiver has only finitely many paths. This is a very important principle. Cycles are what create the possibility of endlessly longer paths. Without cycles, in the finite case, every path must come to an end. Now the previous example becomes even clearer, because we are given the complete list of all its paths. First, we have the length 0 paths, one at each vertex. Then we have the paths of length 1, which are just the individual arrows. And finally, we have the paths of length 2 that can be formed by fitting arrows together. When we list all of them, we get exactly 10 paths in total. This is a nice moment because it shows that, in a finite acyclic quiver, the set of all paths can sometimes be written down completely. Nothing is hidden. Nothing goes on forever. Every legal finite walk can be found and listed. So this example is a concrete illustration of the general rule we just discussed. A finite quiver with no directed cycle has only finitely many paths, and sometimes we can count every single one explicitly. Now let us look at a very important example. Even when we fix the starting point and the ending point, there can still be infinitely many different paths. At first, that may feel surprising. We might think that once the start and end are fixed, the number of possible paths should also be limited. But that is not always true. Suppose we start at A and want to end at C. We can go from A to B, then from B to C. That gives one path. But now imagine that at B there is a loop. Then before going on to C, we can go around that loop once, or twice, or 3 times, or any number of times, so we get many different paths from A to C. They all start at A. They all end at C, but they differ in how many times they go around the loop in the middle. So this example teaches us something subtle. Infinitely many paths do not require infinitely many vertices or infinitely many arrows. A single repeatable part inside the quiver is enough. Now that we have seen many examples, we are ready for the formal definition. A path in a quiver is a finite sequence of arrows. But not just any sequence. The arrows must fit together properly. This means that whenever one arrow is followed by another, the first must end exactly where the second begins. That is the formal condition. So a path is a finite ordered list of arrows, where each step connects correctly to the next one. The word finite is important. A path is allowed to be long, but it must use only finitely many arrows. This definition also includes the earlier cases we saw. Length 0 means no arrows at all. Length 1 means exactly 1 arrow. Length 2 means 2 arrows that fit together. So the formal definition is really just a precise way of saying what we have already been practicing all along. A path is a legal finite walk along directed arrows. Now let us gather the main rule for finite quivers. There is a very clean dividing line. If a finite quiver has no directed cycle, then it has only finitely many paths. But if a finite quiver does have a directed cycle, then it has infinitely many paths. This is one of the most important takeaways of the whole lesson. So for beginners, there is a very simple test. Ask yourself this question: can I keep coming back and continue forever? If the answer is yes, then I can build paths of arbitrarily large length. And that means there are infinitely many paths. If the answer is no, then eventually every path must stop. And in the finite case, that means there can be only finitely many paths. So directed cycles are exactly what create endless path building in finite quivers. Now let us turn this into a practical method. How can we check whether a given string of arrows is actually a path? We can do it step by step. First, read the arrows in order from left to right. Next, look at where the first arrow ends. Then check whether the second arrow begins exactly there. After that, do the same thing again. Look at where the second arrow ends, and check whether the third arrow begins there. Continue this process all the way through the string. If every connection works, then the whole string is a path. But if even one step breaks, then the string is not a path. This gives us a very reliable test. Do not try to judge the whole string at once. Just check one connection at a time. That slow, local checking is the safest way. Now comes a good moment to practice. A very good exercise is to draw a quiver that has a path of length 2 but no path of length 3. That helps us understand how path length depends on how arrows are connected. Another useful exercise is to draw a quiver with 2 different paths from A to B. That helps us see that the same endpoints do not force uniqueness. You can also draw a finite quiver with only length 0 paths. That shows what happens when there are no arrows at all. Then try drawing a quiver with infinitely many paths using a loop. And after that, try drawing one with infinitely many paths using a directed cycle but no loop. These exercises are small, but they train exactly the right intuition. They help the idea settle into the mind naturally. Let us finish by gathering the whole story into one clear picture. A path is a legal finite walk-along arrows that fit head to tail. Every vertex has a path of length 0. Every arrow is a path of length 1. Longer paths are built by placing arrows in an order where each one begins where the previous one ends. And in a finite quiver, directed cycles are exactly what make infinitely many paths possible. So that is the big idea. A path is about movement that is allowed. Not every sequence of arrows works. Only the ones that connect properly. Once that fitting condition becomes natural, the whole notion of path becomes very clear. And this idea will be the foundation for everything that comes next. Please consider liking, sharing, and subscribing if you would like to support the channel and continue this journey of guided mathematical exploration.